Hello students, and welcome to this next edition of our revision sessions of class 11th physics. So we will continue with the same topic of system of particles, center of mass in today's session. So let us begin. So this is the fifth review session for us. In the last session, we were discussing about collisions, and we have seen one-dimensional collisions in detail. So we will continue ahead with collisions today. So let's start with an example problem of one-dimensional collision. So we have a system like this, where the surface is smooth. The block A has a mass of 3 kilograms. The block B has a mass of 5 kilograms. The block C also has a mass of 5 kilograms. Now, A and B are initially at rest. Spring constant is, let us say, 15 newtons per centimeter. So A and B are initially at rest. C is moving at V naught equal to, say, 2.4 meters per second, and makes a head-on collision with A with a coefficient of restitution of 0.5. So we have to find the speed of C, or the velocity of C, and the velocity of A immediately after impact. And we have to find the maximum compression of the spring and we have to find the maximum speed of block B. Okay. So I'll just leave you with a minute to go through the question, then we'll discuss about it. All right, so let's understand this question in more detail. So what happens here is that C comes and makes an impact with the block A. So there is a momentum transfer or transfer of kinetic energy between C and A. But in that impact, the spring does not play any role. And therefore the block B does not play any role directly in the impact because the spring is initially relaxed. So what happens is that immediately after C comes in contact with A, the momentum transfer and the kinetic energy transfer has happened only between A and C, like two independent bodies, and the spring has not played any role whatsoever. So we can treat it like an independent collision between C and A. And once A starts moving after the impact, once it's got some displacement, immediately after the impact, that's when the spring comes into action because the spring compresses. And then it is the system of A plus B plus the spring moving in such a way that the whole system's linear momentum is conserved and the whole system's mechanical energy, including the elastic potential energy of the spring, is conserved. So after the impact, with the kinetic energy that C has given to A as a result of the momentum transfer, okay, the system of A plus B has got some mechanical energy by virtue of kinetic energy, and that mechanical energy is going to shuffle between elastic potential energy of the spring and kinetic energy of the blocks. And alternately, the potential energy will be maximum, then later kinetic energy will be maximum, and so on and so forth. So there will be an oscillation between kinetic and potential energy. So that is what this analysis is all about. Okay. So let's now understand what's happening immediately after the impact. So immediately after the impact, okay, so the spring is still in the zero extension or zero compression state. B is still at rest. Okay. But A has now got some velocity. Okay, and let's say that velocity is V2 and C has got some velocity, let's say that is V1. So V1 is by the collision formula. So for the collision, we will use this relation that basically C and A. So M1 V0 is equal to M1 V1 plus M2 V2 after the impact, and V2 minus V1 is equal to E times V0. That separation velocity is equal to coefficient of restitution times approach velocity. So solving these two, we will get these relations which I'm writing over here. V1 will come out to be mass of C minus E times mass of A. Okay. And V2 will come out to be 1 plus E times mass of C upon sum of the masses into V0. So basically this is coming from solving this. M1 is the mass of C and N2 is the mass of A. Now the mass of C was given to us as 5 kgs and this is given to us as 3 kgs and coefficient of restitution is 0.5. So substituting that here, we will get 5 minus 1.5 divided by 5 plus 3 times 2.4. So this will become the answer of our first part of the question, that immediately after impact, C has a velocity this much. If we take this as our x-axis, and A has a velocity you can see that their separation velocity has become 1.2 meters per second, which is half of the approach velocity. Okay, so I'll just leave you with a minute to understand this, and then let's come to the second part. To find the maximum compression of the spring. Okay, so let's understand. For the maximum compression of the spring, what is happening is immediately after the impact, A is having this velocity, which we saw. X is 0 for the spring, and B is at rest. So after some time, the state of the system is like this, that now the spring is having a bit of compression. Okay. So momentum conservation. So this will give us our first equation. Okay. And conservation of mechanical energy will give us our second equation. This is taking A plus B plus the spring as our system. Same here also. We are taking A plus B plus the spring as our system. Okay. So we have this relation that is over here. So this is our second equation. Now in this we will substitute the condition that when the spring has maximum compression, okay, the relative velocity of A and B should be 0. That should be 0. That means V1 should be equal to V2. Just at that moment they should have the common velocity. So from equation 1 you can see that V1 will be equal to V2, equal to this much. And now we will substitute this in equation 2 to get the value of X maximum. So from this we will calculate the value of X maximum. So this becomes the maximum compression of the screen. Okay. I'll just leave you to analyze this for a little bit. Okay, so the momentum conservation equation, the energy conservation equation, and then the condition applied on that, that at the instant when the spring has maximum compression, the relative velocity of the two blocks should become zero because A has come closest to B. So their velocity in ground frame should be common. So we substitute V1 equal to V2 in this. Yeah. And solving that, this is how we get the value of maximum compression. Now the third part, we want to find out the maximum speed of the block B. Okay. So basically, as you can see, the spring is pushing the block as long as it is compressed. And when it reaches natural length again, at that point of time, the spring stops pushing the block B. So if the spring is in a compressed state, B is gaining momentum. But the moment the spring goes into an extended state, after a while, B starts losing momentum. Okay. So at that point of time, the block B starts losing momentum because of the force acting in this direction. So again, you can see that going from here to here, B is going from a state of acceleration to a state of deceleration. B is going from a state of acceleration to a state of deceleration. So B has maximum speed at the moment when you're going from compression to extension. So when x is equal to 0 for the spring again. Okay. So equation 1 above from momentum conservation was that 3v1 plus 5v2 was equal to 3 into 2.25. That was a momentum conservation equation. And in our energy conservation equation, we will put x equal to 0. So we'll get the relation that this relation. Okay. So now solving this for G2, we will get the required relation. So now the interesting thing is when we solve this, this will give us a quadratic equation in V2. So substituting V1 as 2.25, substituting V1 as 2.25 minus 5 by 3 V2. This gives us a quadratic relation. Okay. Which you will see is quite easy to handle because it's okay. So the 2.25 whole square term will in fact cancel. That's why I said it's easy to handle. So this will become 25 by 6 plus 5 by 2 V2 square minus 22.5 by 2 into V2 is equal to 0. So this will give us two roots. One is of course V2 is equal to 0, which is not the root that we're looking for because that is the minimum speed of V2. Whereas the maximum one, that is the one that we're looking for. And that is equal to V2 equal to We approximate it up to second place of decimal. So this will become the maximum speed for the block. So this is an example of, again, application of collision in a longer question which involves momentum conservation and energy conservation put together. As is expected for your solving of the JEE advanced level questions. Leave you with a minute to go through this. Okay, students, so let's move on to the next part of collisions. So next up, we will take a quick recap of the concepts of collision of a particle with a rigid surface, which means a fixed surface. Okay, so the example can be, like a spherical body bouncing off a floor, or the collisions of carom coins on the wall of the carom table, the carom board. So if this is a rigid surface, this is like a fixed vertical wall, and the XY plane, so this is in the YZ plane, and the XY plane is a smooth horizontal surface. So this plane here, there is a smooth horizontal surface. So if a particle like a tiny sphere or a disk impacts this with a velocity which is along the normal to the wall. So if a particle of mass m makes an impact along the normal to the wall, then what we can understand is that during the impact, the collision impulses that act, they act in this manner. So as the particle comes and hits the wall, it will apply an impulse on the wall in this sort of direction, and the wall will apply an equal and opposite impulse in this sort of direction. So this is the collision impulse J. Okay, that acts like this, and as a result of that, the particle will recoil, but along the same axis. So this also becomes like a one-dimensional situation, because the axis of motion remains the same. Only the direction of the particle gets reversed along that axis. So after impact, what we'll observe is that the particle has a velocity in this sort of direction. We can say that V will become E times V naught, because E being the coefficient of restitution. Okay. E is equal to the separation velocity ratio with respect to the approach velocity. So that is V upon V naught. Okay. So that is a concept over here, and obviously E is okay. E equal to 0 will be the perfectly inelastic collision, and E equal to 1 will be the perfectly elastic collision. Whereas E equal to 1, as you know, is the perfectly elastic case. Okay. So this particular situation that we saw here, this is called the normal impact, because the direction of the impact velocity is along the normal, it's along this perpendicular axis. So this example is what we call the normal impact. Now we can also have a situation where the impact is oblique. So we'll discuss about that next. So if we have a situation like this where the direction of the particle's impact velocity is like this. Okay. So it is at some angle with respect to the normal axis. So this angle is theta naught, let's say. Okay. Then this is an example of what we call the oblique impact. So what happens for the oblique impact is that so first of all, during the collision, we come to after the collision afterwards. So this is our normal axis. So during the impact, the impulse that is acting along on the particle is along this axis. So that is the direction of the collision impulse. It is not along the initial axis of motion. So therefore, what happens to the particle after the impact is that in general, the particle goes off in some other direction like this. Goes off with a velocity v at some different angle theta compared to what this angle was, theta naught. Okay. So now we can see in this that the approach velocity is nothing but the normal component of v naught. So this is the direction of the normal axis. Okay. So you can see that this component, so that is equal to v naught cos theta naught. And here we can see that the separation velocity is again the normal component of v. So that is equal to v cos theta. So coefficient of restitution being separation velocity's ratio with respect to approach velocity. So from this relation we can see that v cos theta is e times v naught cos theta naught. This is the important relation. Okay. And of course, also we can see that tangential to the wall, the surface of impact, okay, the impulse on the particle is zero. So tangential momentum is conserved of the particle, that is conserved. Okay. So here you can see that the tangential component of momentum is this component, the one parallel to the wall. So it is mv naught sine theta naught. And here you can see that the tangential component is mv sine theta. So from this relation, we get that v sine theta is equal to v naught sine theta naught. So this becomes our second equation. Okay, so now from equation 1 and 2, we can see that v's final value is square root of e v naught cos theta whole square plus v naught sine theta naught whole square. So that comes out to be v naught into square root of e square cos square theta naught plus sine square theta naught. Okay. And dividing the two equations, we can see that tan theta comes out to be tan theta naught divided by e. Okay. Remember, e is something that can range from 0 to 1, inclusive of both the values. So from this result, what we can see is that for e equal to 1, perfectly elastic collision, we get the result v is equal to v naught, which means that kinetic energy is conserved. Okay. There's no dissipation of energy, and theta is equal to theta naught. So it is almost like an angle of incidence is equal to angle of reflection kind of situation. Okay. But for coefficient of restitution less than 1, we get v is less than v naught and theta is greater than theta naught. So there is loss in kinetic energy, and there is divergence of the angle with respect to the normal. Okay. And in the extreme case, for e equal to 0, which is the perfectly inelastic collision, what happens is that v becomes v naught sine theta naught and theta becomes 90 degrees. So the particle sticks to the surface, slipping tangentially. Okay. So let us look at an example of the application of this here. Okay, so let us look at a very typical example of collision of particle with rigid surface. And that is something like this. When we have a projectile which is repeatedly bouncing off a surface. So let us say we have got an example of a particle fired at a speed of 50 meters per second at an angle of 53 degrees to the horizontal, and it makes an impact here with a coefficient of restitution of 0.75, and thereafter it bounces like this. Okay, so we have to, so it first bounces at the point, let's say A, and then the second bounce happens at the point B. So the first thing we have to do is we have to find the velocity just after impact at the point A. And secondly, we have to find the range and maximum height between first impact at A and the second impact at B. Okay. And then we have to find the velocity just after the second impact at B. Assume same coefficient of restitution. Okay. So I'll just leave you with a minute to analyze this question and go through it. Then we'll discuss how to solve it. Take the value of G as 10 meters per second square. For the second part, we're going to require that value. Okay, so let's understand this question in detail. So what we can see here is that if we take the components of the initial velocity, so the initial velocity being 50 meters per second and this being 53 degrees, we will see that the horizontal component of the initial velocity is 30 meters per second and the vertical component is 40 meters per second. Okay. So as a result of that, when this particle or sphere or whatever comes and makes the first impact at A, okay, the impact velocity has vertical component of 40 meters per second, which is the normal component. So that in fact becomes the approach velocity, and the horizontal component is conserved, so it's 30 meters per second, and this is the tangential component. Okay. So remember that the tangential component remains conserved, but the normal component is the one that gets reversed in direction, and in this case suffers a decrease in magnitude because the collision is inelastic. It is having a coefficient of restitution of 0.75. So because of that, immediately after impact, what will happen is that this new component of velocity, let us say Vy prime, will become E times Vy. So it will become 0.75 into 40 or 30 meters per second. Whereas this component of velocity, let's say Vx prime, that remains conserved. Okay, because the tangential component is conserved, and V separation is equal to E times V approach. This is a concept that we are applying here. Okay. So as a result of that, we can see that the velocity immediately after impact, let's say V prime, so that V prime is 30 root 2 meters per second at theta equal to 45 degrees with respect to horizontal. So this becomes the answer to our first part. The velocity just after impact at the point A. Okay. You can express this as a vector also. So now as far as the second part is concerned, the range from A to B, etc. That's very easy to calculate. So you can see that maximum height will be okay. So the range will be 180 meters and the maximum height it will reach is going to be 45 meters. And then we can see that at B, the impact velocity will be like this. This is the same as the projection velocity from the point A. So immediately after impact at B, this will become E times the approach velocity. So that is going to be 3/4 of 30, 22.5 meters per second. Okay. So the velocity V double prime Okay, so this will be the speed and this will be the velocity, etc. Okay, so with this, we conclude today's session. And next session, we will look at oblique collisions between particles and then some more applications of system of particles concept, including variable mass system, etc. So until then, wish you all the best and thanks for attending.